So we're going to use Gibbs equation, and we're going to explain why melting ice doesn't happen at a low temp. So for our Gibbs, we've got change in free energy is equal to change of the enthalpy minus the Kelvin temperature times the change in the entropy. And so if we're talking about it being at a low temperature, that means my temp part is low. What I'm trying to prove is that this is not a spontaneous reaction. So what does the sign need to be for the delta G? It needs to be positive. If this is a positive value, then ice won't melt at a low temperature, which obviously we already know. And why is... Okay, so let's talk about the heat for a second. What happens when I'm melting ice? You're putting energy into it, right? And so nature doesn't like that. Nature doesn't want energy to be put into something. But when energy gets put into something, that means the delta H is going to be a positive value. And my delta S, what is happening to it? Oh, wait, no. Or I'm melting it? Yeah. What's happening to my S in this case? If I'm trying to melt ice. I'm going from solid ice to liquid ice. So what would happen to the entropy? It'd be more chaotic, so the number would be bigger. So this value here is that's gonna go up. Great. So what I have is my H becoming more positive and my S becoming more positive. So those two things are fighting each other. So what I have to do is this term and this term are at odds with each other. So this term is positive, which is going to tell me that it's not going to melt, and this one is positive, which is telling me it is going to melt. Except what's controlling this term here? A temp. So what ends up happening is this term here is too small to overcome this term at a low temperature.
And the change in S is the entropy, right?
Correct. So I guess your answer for this one is if it was a larger value, then it would be able to overcome the positiveness of the delta H and still be negative, but it's not in this case. So what are the hand warmers that skiers use?
Iron.
It's just regular old iron in a powder form, mixing with oxygen. I don't know what that was, but what are we doing here? Cool. I have no idea why it's doing that. Maybe if I drag it over with a mouse, come down here. All right, let's see if that works. So we just have oxidation, we just have rusting of the iron. Okay, so what we know is it's a spontaneous reaction, and it gives us a delta G that's negative. So how do I know that the delta G is going to be negative?
T times change in S.
Yep, that is large. So let's talk about the S. What happens over here?
It went from kind of organized to not that organized.
The most important thing that happened is I had pure iron and I had pure oxygen, and that's organized. that those elements are separated as pure substances. And now I've gone and I've mixed them together. So because they were mixed together, that made the entropy go up a lot. Even though I had a gas turn into a solid, I already had a solid. I had a solid and a gas, and now I've just got a solid, but it's a solid of everything mixed together, which overrules just the state change. So I know for this, my S is going to be a positive value because this got mixed up. And then what do you know about the delta H? Right, the end is smaller, so that means this is a negative value, right? It's giving up heat. I know it's giving up heat, otherwise I wouldn't be putting these things in their gloves to keep their hands warm. So if I've got heat given off by this reaction and the components of the reaction become more disordered, then no matter what, this has to be a delta G that's negative. So under no circumstance will this ever not be spontaneous. It's spontaneous under all conditions. Okay, how about this disappearing thing? So you see like a possum or a squirrel or something get hit by a car, or the result of one getting hit by a car. County sometimes picks it up, sometimes they don't, but it eventually disappears. So where's it go? Okay, so a crow comes by and eats it, sure. Microscopic organisms come by and eats it. So the end result is what happens to this, I don't know, squirrel. Right? Entropy goes up a lot. So you just wait long enough, that thing's going to completely decay. It doesn't matter if there's microbes there or not, eventually it'll decay. It could take a hell of a lot longer if there are no microbes around, like animals being drowned in bogs. I don't know if you've seen any of those things. They've like pulled bodies of dogs and cats and humans out of bogs, and they just look thick. Like they could be underneath that bog, swampy mudness for like 200 years, and you pull them out. Nothing's happened to them. Their skin looks perfectly supple. It actually is supple. You can push on it. It has bounce back to it, but it hasn't decayed because, tell me about the bog. Tell me about the microbes in the bog. It's not conducive to microbes. It's anaerobic microbes, and there aren't any aerobic microbes that do the breaking down. So it just persists. So if you're watching the second Lord of the Rings movie, second one, Gollum takes him through the nasty bog, and then there are those people in the water. That's exactly what they would look like, even after hundreds of years. If it's an actual bog where it's anaerobic, then they'll persist. I mean, they basically just come out and look like they've been blanched. No redness to them, very gray and discolored like that. But other than that, everything's intact.
I read this one thing that said is like there's a lot of spontaneous reactions happening in like microstates in organic matter, and that's what breaks itself down.
Sure, like another example of this happening that's not microbe related is somebody who's lactose intolerant. Like what's the bad thing about being lactose intolerant? Yeah, but what's the bad part about not being able to break down lactose? It's a very energetic organic molecule. It will break itself down. So what's the poor side effect? Gas buildup. So it's either really uncomfortable or annoying. I mean, it can actually be very painful if somebody who hasn't knows they're lactose intolerant and somehow some lactose slips into their diet. They know it in about 5 minutes because it feels like somebody's got a bicycle pump inside of them pumping themselves up. That reaction is going to happen because it's warm and wet, and it doesn't, in that environment, it wants to break down into different substances. And so the squirrel that got run over, it's basically just turning into gases. Eventually it's just going to be gone. Okay, so when we talked about this kind of problem in the notes last class, what did I say to look out for? Yeah, so I got a joules, I got a kilojoules, and I got Fahrenheit, and I got Kelvin. So I got to do some unit conversions before I can actually do any math with this. So I think the easiest thing to do, the first easy thing to do is just make this 2200 joules per mole, negative. And then we'll convert that 62 minus 32 times 5/9.
287.
What's that though? 150 divided by 9. Sure. I'll just make it 17 degrees Celsius, and then 273. Right. You said 290?
I think I said 287, but yeah.
All right, that's good. Okay, so I've got that Kelvin temperature, and I've got these joule or kilojoules, joules thing set up. So my delta G is going to be equal to negative 2200 joules per mole minus 290 K. And then this is 9 joules per mole Kelvin. So I'll get my K's to cancel out, and then everybody will be in the same units. And this will be 2 per mole. So negative 2200 minus 290 times 9. So this will be negative 4810 joules per mole. Could we have answered this question without doing the math? The question only asks, is this reaction spontaneous? And the answer is yes. And I know it's yes because it's becoming more chaotic because the S is positive, and it's losing energy because the the change in enthalpy is negative. So I didn't have to do the math. I could have just said, yep, has to be. There are no circumstances where this would not be spontaneous. Okay, how about this Boltzmann's liquid state? What do we got here?
Solid block order to them, so their entropy level is less than the liquids.
When we look at a crystal solid, I mean, it doesn't matter if it's just like a metal or an ionic substance or something like that. Everything's ridiculously organized. It's in its center phase structure, body phase structure, one of those cubic units, and everything is based off of that, and it looks the same all the time. And then when we've got the liquids, I mean, they could be anywhere, right? Where's that guy? Where is he in relationship to the 4 atoms around him? That's where he is right now, but where could he be? He could be right here in a moment, or right here in a moment, or right here in a moment. So the number of different possibilities for organization of all the atoms is infinitely greater, not infinitely greater, but much greater because they're allowed to move around. So the more possible places I could put all the atoms relative to each other causes the entropy of that system to be much higher in the liquid state than it ever is going to be in the solid state. I suppose we could say, unless we're talking